double-acting cylinder is hydraulically driven in two directions. Pressure oil enters at the cap end of the cylinder to extend it. Oil is forced from the rod end and returned to tank. To retract the cylinder, high-pressure oil is directed to the rod end.
Telescopic cylinders. Most telescopic cylinders. Figure 74. A single acting. Telescopic cylinders consist of a series of nested tubular rod segments called sleeves. Each sleeve extends individually during extension. There may be 2, perhaps 3, and possibly up to 5 sleeves in a cylinder. A long working stroke and a short collapsed length result, making them ideal for applications such as industrial lift trucks and large tilt-fed or dump trucks. An inherent feature of telescopic cylinders, due to the sequencing smaller diameters of sleeves, is a reduction of force capability and an increase of velocity during each succeeding stage. Telescopic cylinders may also be double-acting, see figure 75, although these are not too common. Because of the very small areas involved in the retracting phase, retracting forces are quite low. Double-acting telescopic cylinders are typically used in refuse haulers as high compaction forces, and a long stroke are required, but retraction force requirements are very small. Modified cylinders. There are many special configurations of linear actuators that customize them for particular applications. Some of these are proprietary to specific machine manufacturers, and are not typical beyond those applications. Others, though, are more generally available and may be considered standard options. Counterbalance valve. It frequently can be advantageous to incorporate some specific valve requirements within the cylinder, usually into the cap end head. The popularity of screw-in cartridge valves has made some of these features relatively easy and inexpensive to accomplish, although the counterbalance valve, figure 76, is probably the most popular type of integral valve. Other types such as directional control, flow control and sequence valves can be found. Cushions. Frequent and abrupt end of stroke stops can damage a cylinder. Cylinders that extend and or retract at high speed can fail catastrophically in just a few strokes. Cylinder cushions are a fairly common feature on mobile equipment that helps to slow the piston down near the end of its stroke and reduce the impact. Cushions may be found on one or both ends of a cylinder to act as hydraulic brakes during cycling. Figure 77 shows one type of cushion used on the retraction stroke. Stroke limiting. Although a simple stop tube, figure 78, can be used to limit the travel of a cylinder, it is frequently desirable to externally adjust the stroke travel. Stroke limiting. This is done with a stroke control valve similar to that shown in figure 79. The stroke is adjusted by locating the stop flange on the cylinder rod to activate the stop valve. Different retraction positions. Reversing the flow direction will compress the valve spring and allow the cylinder to extend. Thermal relief valves. Cylinders that have cooled down and are then subjected to heat from the sun or other source may be damaged by the resulting fluid expansion. Extremely high pressures can be developed as the fluid expands, unless there is a way to relieve the pressure and drain off a small amount of the fluid. A small integral relief valve or cartridge, figure 80, set much higher than system pressure will accomplish this task and prevent damage to the cylinder. Cylinder ratings. The ratings per cylinder include its size and pressure capability. Principal size features of all: piston diameter or inside body diameter, piston rod diameter and stroke length. The pressure rating is based on the size, design and materials used, and is established by the manufacturer. Refer to the cylinder nameplate or the manufacturer's catalog for this information. Graphic symbol hydraulic cylinder. The symbols for a few basic types of hydraulic and pneumatic cylinders are shown in figure 81. The rod size and length of stroke is not reflected by the symbol's dimensions. At the top, 2 examples of single-acting cylinders, or cylinders which can only be pressure activated in one direction. In the center is a common example of a double-acting cylinder, while at the bottom an example of a double rod end cylinder similar to the steering cylinder used on the backhoe loaders and wheel tractor scrapers is shown. The basic symbols for cylinders can also be modified to show other features and functions. Figure 82 has two examples of modified cylinders, when the rod bore diameter is important to the function of the circuit. The left symbol shown should be used, which depicts a large diameter rod. The right symbol represents a pressure-intensifying cylinder used for pressure multiplication. The two symbols in figure 83 represent fixed and adjustable cushions or snubbers. These are used to slow piston and rod travel near the end of the cylinder stroke. The top symbol has a fixed cushion in both directions of travel. The bottom symbol is an adjustable cushion on the extension side only, denoted by the variability arrow drawn through the cushion block. Note the cushion block symbol is only on the rod side of the cylinder. To the left we see a cutaway drawing of a cylinder with fixed cushions on both the extension and retraction sides. Another example of how a cylinder may be cushioned is seen on the next slide. Rotary actuators. Linear actuators convert fluid power to linear motion. Rotary actuators convert fluid power to rotary motion. Fluid is pushed into the inlet of the rotary actuator and causes the output shaft to rotate. Resistance to rotation by an external load creates pressure in the hydraulic circuit and in the inlet of the motor. Gear type. A cross-sectional view of an external gear hydraulic motor is shown in figure above. This design is referred to as external gear design because the gear teeth are machined on the outside of the gears. One of the gears will be connected to an output shaft, and the other will be an idler gear. Not shown in the illustration are the side plates, which create a sealing wear surface on the sides of the gear set, and are similar to these used in a gear-type pump. Gear motors operate because of a pressure differential, or dP, between the motor inlet and outlet. This pressure differential acts across the gear teeth, creating a force that rotates the gear. Vane Motors. A cross-sectional view of a balanced vane rotating group is shown in figure 85. The elements shown in the view are the cam ring or displacement ring, rotor and vanes. The output shaft of the motor is connected to the center of the rotor. The vanes slide in and out of the slots in the rotor so as to make contact with the cam surface. A form of spring, either a spring clip or a small coil spring, is placed under the vane to cause it to stay against the cam surface. Figure 86. Dot. In addition, inlet fluid is also ported under the vane so as to balance the pressure between the top and bottom, and prevent pressure from pushing the vane back into the slot. Fluid entering the motor will pressure two opposite sides of the rotor assembly, and return fluid will exit two opposite sides. This way, equal pressures are always opposite each other, balancing forces across the rotor. This relieves any loading on the drive shaft and bearings caused by internal pressures and forces. Figure 87 shows how the differential pressure across the vane will create a force on the vane. The amount of vane that is exposed to pressure will determine the magnitude of the force. Force equals pressure times area, comma, and the distance from the center of the exposed vane area to the center of the drive shaft will determine the torque that is generated. Therefore, the torque output of a vane motor is dependent upon pressure, size of the vane, height extending above the rotor and width, and radius of the rotor, distance from the center line of the drive shaft. Inline piston motors. A cutaway view of an inline piston motor is shown in figure 88. The components that make up a piston motor rotating group are a cylinder block, pistons and shoe held down plate, swash plate, valve plate, and drive shaft. The drive shaft is connected by splines to the cylinder block, and the shoe are held down to the swash plate by a hold down plate. As fluid is forced through the valve plate into the cylinder block, pistons are forced out of the cylinder block, causing them to slide along the angled swash plate. This causes the cylinder block to rotate along with the pistons, turning the drive shaft. As pistons are forced back into the cylinder block by the swash plate, fluid is forced out through the valve plate and back to the reservoir. The amount of torque that the motor will deliver is based on the force of the piston, pressure times area, the radius of the piston circle, force times distance, and the angle of the swash plate. The higher the swash plate angle, the greater the torque output for any given pressure. Bent axis piston motors. A cross-sectional view of a bent axis piston motor is shown in figure 89. The main elements are a cylinder block, Pistons and shoes drive shaft and flange, a universal link and a valve plate. The piston shoes are lodged in the drive shaft flange, and the universal link maintains alignment between the cylinder block and the drive shaft so that they turn together as fluid is forced through the valve plate into the cylinder block. Pistons are forced out of the cylinder block, forcing the drive shaft flange to rotate. This causes the drive shaft to rotate along with the cylinder block and pistons. Pistons are forced back into the cylinder block by the drive shaft flange, and fluid is forced out through the valve plate and back to the reservoir. The entire operation is much the same as the inline piston motor, except that the cylinder block and piston assembly is angled instead of a swash plate. The amount of torque that a motor will deliver is based on the force of the piston. Pressure times the piston cross-sectional area, the radius of the drive shaft flange, force times distance, and the angle of the cylinder block. The higher the cylinder block angle, the greater the torque output for any given pressure and piston size. Graphics symbol rotary actuator. The symbols used for motors are very similar to those used for pumps. Rather than creating flow or converting mechanical energy into fluid power, though, motors do just the opposite and convert fluid power into mechanical energy. This is shown by using the same basic component symbol as a pump, but with the energy triangle reversed pointing inward. This indicates that fluid power is taken into the component as the triangle's orientation shows. All other supplemental component elements used for motors are the same as those used for pumps. It is important to remember that graphic symbols such as these for pumps and motors do not indicate the kind of pump or motor, opening parenthesis, the vane or piston type, being represented. The symbols only designate the type of pump displacement and method of operation. Directional control valves. Directional control valves, DCV, are used to direct oil into separate circuits of a hydraulic system. Figure 91. The maximum flow capacity and the pressure drop through the valve are the first considerations. Directional control valves may be interfaced with manual, hydraulic, pneumatic and electronic controls. These factors are mostly determined during the initial system design. Directional control valves direct the flow of oil in the hydraulic system. This is a means by which the operator controls the machine. The directional control valve directs the supply oil to the actuator in a hydraulic system. The valve body is drilled, honed, and sometimes the bore is heat-treated. The inlet and outlet ports are drilled and threaded. The valve spool is machined from high-grade steel. Some valve spools are heat-treated, ground to size and polished. Other valve spools are chrome-plated, ground to size and polished. The valve body and valve spool are then mated in assembly to the design specifications. When assembled, the valve spool is the only part that moves. Simple spool DCV. Valve centered. Oil to the cylinder is blocked by the position of the spool. Valve shifted left. Oil can now flow from the P port to the cylinder port, and oil can also flow from the non-active side of a double-acting cylinder through B to tank. T. Valve shifted right. Oil can now flow from the P port to the cylinder B port. Oil can also flow from the non-active side of a double-acting cylinder through port A, through the drillings in a valve to tank. T. The spool shown in the figure 92 operates a double-acting cylinder by directing flow to either end of the cylinder. Ports A and B for the ports to the cylinder. Port P is pressure oil from the pump. Port T is drain oil to the tank. Open center directional control valve. Open center valves have a passage designed in the valve body casting that allows all inlet flow, when the spool is in neutral or center position, to pass through a bypass area. This flow either exits the valve back to the tank or is available for another valve connected in series to the first valve. The advantage of an open center valve is that there is little work done by the pump. When the valve is in neutral, minimal pressure is built up. The main disadvantage is that there is a small time lag when the valve opens, as pressure needs to build up in all of the circuit. Figure 93 shows a cutaway diagram of a typical open center directional control valve in the hold position. In the hold position, the pump oil flows into the valve body around the valve spool and returns to the tank. The valve spool also blocks the oil in the line to the rod end and the head end of the cylinder. The above example of a directional control valve also contains a load check valve. In the held position, the load check valve has spring tension behind it to keep the valve closed and prevent drift from the implements attached to the cylinder. Figure 94 shows the valve spool at the instant the spool is moved to the raised position. When the valve spool is moved to the raised position, the valve spool blocks the pump oil flow to the tank. However, pump oil flow is open to the load check valve. The valve spool also connects the cylinder head end to the oil behind the load check valve and the cylinder rod end to the tank passage. The load check valve prevents the oil in the head end of the cylinder from flowing into the pump oil passage. The blocked pump oil flow causes an increase in the oil pressure. This action prevents drift of the implement until pump pressure builds up. The increase in pump oil pressure overcomes the pressure behind the load check valve and unseats the valve. The pump oil flows past the load check valve and around the valve spool to the head end of the cylinder. The oil in the rod end of the cylinder flows past the valve spool to the tank. The reverse applies when the DCV is placed in the lower position. Check valve. The purpose of a check valve is to readily permit oil flow in one direction, but prevent check oil flow in the opposite direction. The check valve is sometimes called a one-way check valve. Most check valves consist of a spring and a tape of seat valve as in the figure above. However, a round ball is sometimes used instead of the tape of seat valve. In some circuits, the check valve may be free-floating, has no spring. In the valve on the left, figure 96, when the pump oil pressure overcomes the oil pressure in back of the check valve plus the check. The valve slight spring force. The check valve opens and allows the oil to flow to the implement. In the valve on the right, when the pressure of the pump oil is less than the oil pressure in the implement, the check valve closes and prevents implement oil flow back through the valve. Closed center directional control valve. Closed center valves do not have a bypass passage and block all flow through the valve when the spool is in the neutral or center position. These types of valves are used with variable displacement pumps where system flow in the neutral position does not exist as the pump will be in its cut-off or standby position. Figure 97 illustrates a typical closed center mobile spool valve. Closed center valves can also be a combination of inlet spool with outlet pockets, or inlet pockets with outlet pockets. These designs feature independent control of the valve inlet from the valve outlet with resulting flexibility to the control features of the valve. Figure 98 shows a multiple spool open center valve with a centrally located bypass passage. In figure 98, valve section 1 is in the neutral position and the bypass feature is porting fluid. The bypass pressure setting to the following valve sections. Valve section 2 illustrates the bypass operation with the valve shifted out for flow through port B. And, in section 3, flow to port A before the flow in either section 2 or section 3 can be usable. The bypass must first be restricted or dosed down, or else the fluid will continue through the bypass and do no work. Flow takes the path of least resistance, as illustrated in section 2. When the spool is shifted far enough, the bypass will be completely shut off and the flow will then pass to the work port. Port B, return flow, coming back through the return line, is free to flow to the outlet or tank passage to the reservoir. The reverse of this is illustrated in the third section. Multiple spool valves are typically either series design or series parallel design. Series design valves are typically the lowest cost and are used in many cost-sensitive applications, where maximum system pressure is not very high, generally 2000 psi, 13,790 kilopascals, or less. All of the flow is available to each of the valve sections, but at the highest pressure demanded. As such, they are not advantageous in applications where system heat level or energy consumption is critical. Series parallel designs. Figure 98 are the most commonly used type of multiple spool valve. While they permit independent pressure operation for each section, oil flow will follow the path of least resistance, and the section with the lowest pressure will tend to have all the flow unless the operator is able to minimize this through the use of metering.